Hi class, we're on to section 11.2. We're going to explore the idea of these positive definite matrices a little bit more. We'll do a little bit of factoring. We'll have a couple of theorems to let us know exactly when something is positive definite or not, besides looking at just the eigenvalues as we described in the previous video. Okay, so let's start off with the definition. Okay, so a n by n symmetric matrix, which we can call A, is positive definite if the corresponding quadratic form Q of x, which is x transpose A times x, is itself positive definite. Okay, so if you want to check to see whether or not your matrix is positive definite, you can look for the eigenvalues, or you can put it into its equation form. And if that equation form has nothing but squares going on everywhere, then obviously it's always going to be positive, because you can't take the square of something and get a negative value out, right? So if everything is being added and everything is a squared term, then you should definitely know that it's always positive. And if it's always positive, if it's positive definite, then our matrix is also positive definite. We have analogous definitions also for negative definite and indefinite. Okay, so if it's clear from your equation that you get from the x transpose AX that it's always going to give you a negative value, then you're going to be negative definite. And if it's obvious to see that it's going to alternate between positive and negative values, then it's an indefinite form. Okay, so you can use this equation to talk about the matrix that produces that equation for you. All right. So here goes the theorem. If A is symmetric and a positive definite matrix, okay, then A is non-singular, meaning that if you're positive definite, okay, you are positive eigenvalues. If you look at your quadratic form and it's obvious that it's always positive, obviously you have to be a symmetric matrix and even in order to even be positive definite, right? But basically what this is saying is that if you are a positive definite symmetric matrix, then you are invertible. Okay, remember, singular means that there's no inverse. Determinant is 0. So this means that the determinant is non-zero and you can invert your matrix, right? So A non-singular means you are an invertible matrix and that your determinant is positive. Okay, because it's positive definite means that it's positive. So remember, invertible just means that determinant is non-zero, but this positive definite portion of this theorem guarantees that the determinant is positive. Okay, this does not mean that if you check the determinant first and it's positive, that you're positive definite. Okay, this determinant being positive, this is a result of our matrix being a positive definite matrix. It is not a method for us to check for positive definiteness. Okay, so the the inverse of this is not true. Okay, the transposition. So if we're symmetric positive definite, then the determinant will be positive. We cannot say it the other way around. Okay, so let's do an example to show this little asterisk portion of it, right? So let's consider this matrix A. It's -2, -1 on the main diagonal, zeros everywhere else. Very, very obvious that this is symmetric, n by n. Okay, the inverse definitely exists. Okay, the determinant here is positive, right? I have a positive determinant. However, if I look at the eigenvalues here, okay, positive determinant, the eigenvalues are really, I don't even have to show all this, but it's obvious that it's just the, it's literally the exact values of the main diagonal, okay, because it's a diagonal matrix. I have negative eigenvalues. So a positive determinant, but negative eigenvalues. That means that this matrix has a positive determinant, But since both of these are negative, it's a negative definite matrix. Okay, so that's going against this theorem because I tried to verify that this was positive definite by looking at the determinant, and I cannot do that. Okay, again, being positive definite means that the determinant of A is positive. I cannot do, sorry, the converse is the word I was looking for. I can't do the converse of that, which is look at the determinant and then talk about the definiteness, right? We can, but there's some conditions for that. We're not there yet, right? So let's move on to another definition. Okay, so again, this was a counter example, right? This was verifying this star term. It was not a counter example to the theorem. You can't counter example a theorem, right? But we were showing that this asterisk portion here is true, right? This little note that I had for you guys. That's what this example was for. So let's move on to a definition. Okay, so let's say we have a matrix A. So this is just the term-by-term entry notation, right? So we're looking at each entry for this matrix A. So this is the entry in position 1, 1, 1, 2, etc., etc. So it's an n by n matrix, right? Then what we call the leading principal submatrices of this matrix A is given by, and what we're going to do now is we're going to look at the small submatrices that is formed by starting in the corner. So our first leading principal submatrix is just the matrix formed by this single entry A11. Okay. My second principal submatrix is going to be the next sized square starting here. So this 2 by 2 in this corner is my A2 principal submatrix. For A3, it's going to be the first 3 rows and first 3 columns. Okay, and I'm going to do this forever and ever until I reach n. So the A sub n principal submatrix is going to be the same as my matrix A. Okay, so this definition is important because this definition is how we figure out by using determinants about the positive definiteness of a matrix, right? So that's our next theorem. Okay, a symmetric positive definite matrix A has leading principal submatrices of A1, A2, up to AN, which is A, that are also positive definite. Okay, so the principal submatrices are also going to be positive definite, right? So the next theorem is that a symmetric matrix A is positive definite if and only if the leading principal submatrices, A1, A2, so forth, satisfy the following condition, and that is that all of their determinants are positive. So if I want to check to see if something is positive definite and I don't want to find the eigenvalues or check the quadratic form, what I can do is look at the determinant of each of these submatrices. Okay, so for instance, if I had a 3 by 3 matrix, I would just look at the first term. Is it positive? Yeah, so the determinant of that would be positive. I would look at the next one. The 2 by 2 determinant is super easy to find. I can check that probably in my head without even writing anything on paper to see if it's positive or not. And then I can calculate the 3 by 3 and figure out if that is positive or not as well. And if all of those are positive, then that 3 by 3 matrix would be positive definite. Okay, so I can use the determinants to check, but in order to use the determinants, I'm using the determinants of the leading principal submatrices. Okay, so I'm doing a bunch of submatrices up until I have my entire matrix, right? So of course, if you have like a 10 by 10 matrix, and that can be kind of tedious. Generally, we don't do anything really more than 3 by 3 in this class unless it's on your homework. Sometimes they throw you some larger stuff. So that can actually be pretty easy to check in respects to versus finding the eigenvalues of a 3 by 3. Sometimes that can be kind of difficult, right? So here, if this is true, okay, then A can be reduced. So if if this is true, then A can be reduced to row echelon form without using any row interchanges and with all of our pivot elements being positive. Okay, so all the places where the pivots are going to show up, they will be positive values, right? So basically the A11, the A22, and the A33, those should all end up being positive values. So this is important because this is going to allow us to do what's called an LU factorization. Now, we skipped over this in this class because at the time, as I was subbing, it was not in what was told to me to be covered, so we're going to cover it now, and we're going to expand on that topic as well because it comes up again now in this section. So I'm going to teach you how to do this at this point. But an LU factorization is actually fairly simple. There's not a lot that you have to do in the way of like eigenvalues and eigenvectors and things like that. Okay. Now it is a step-by-step process. I'm sorry, but the steps that I laid out, they'll sound confusing, but when you put them into practice, it's not that bad. Okay, so let's go ahead and do an example. But before we do an example, let's talk about really quickly just what it is I just talked about, which is the LU, which we're going to expand into an LDLT factorization. Okay, so matrix A can be uniquely factored as A equals LDLT. So we really only need two matrices, an L and a D. And the third term of this is going to be the transpose of the first one. Okay. Here, this D matrix is actually going to consist of the eigenvalues, right? But we're not going to find this by doing a regular method of finding eigenvalues. The reason why this turns into eigenvalues, though, we'll discuss once we get there, right? So here, L is lower triangular, and it's going to have ones on the diagonal. Okay. D is going to be a diagonal matrix with positive diagonal entries, and it just so happens that those entries will also be the eigenvalues, although that's not the way that we put this together. Okay, so let's go over the process here. Okay, so what we're going to do is we are going to build this L matrix, this lower triangular matrix that has ones on the diagonal, right? So just think about this. It has to be lower triangular. That means above the diagonal, everything is 0. Okay. Along the main diagonal, everything is going to be 1, right? So just knowing that is going to make these steps we're going to outline a little bit easier to follow. Okay, we are going to build the rest of the entries one column at a time. So we know that whatever entry we're on for the main diagonal is going to be 1. Anything above that will be 0. Then we're going to talk about how we're going to fill the stuff below the main diagonal. That's what the process is all about. And again, we do that one column at a time, right? So first thing I want to do is we're going to say A1 is the first column vector of A, okay? And then I'm going to call this L sub whatever vectors the associated column vector in L, okay? So what I'm going to do is I'm going to take the first column vector in A, and I'm going to divide the entries by whatever value the first entry is. So in the pivot position, so remember the pivot position are those values along the main diagonal. Okay, so I'm going to take the first entry, which is going to be A11, right, from my first column. Okay, and when I divide all the entries, I'm not writing those values as I start to row echelon form A. What I'm going to do is those values that I get from dividing the first column of A by the first entry in A, that will be my L1 vector. Okay, so my A1 vector is going to stay unchanged, but the way that I build the L1 is I take that A1 vector and I divide it by whatever the first number is, and that's what L1 is going to be. Okay, so as of right now, that first column in A would be unchanged, but L1 would look like all of those entries from A1, but divided by that first A11 term. Okay, so then the next thing I'm going to do is I'm going to zero out the values below the pivot position in A1. Okay, so everything below A11, I'm gonna divide. I'm sorry, I'm gonna zero it out by using a row operation. Okay, I am not gonna divide everything by 1. I don't care about the first term here being 1. In fact, I want it to stay whatever it was. So for instance, if the first entry in my matrix, let's come back here. If the first entry in my matrix was 12, okay, I'm going to take all these things and I'm going to divide it by 12, and that result will be L1. Okay, I'm going to keep this as 12. I am not going to turn it into a 1. I'm going to keep this as 12, but all the entries below here I'm going to turn into 0 by using row operations. But this will remain 12. This does not change. I don't need to turn this into 1. I just need everything below it to go to 0. So all these other vectors would change. Okay, and so that's where we are right now for step 2. Okay, and again, I do have an example of this, right? But I'm going to go backwards instead of forwards to show you how this works. So I am basically going to repeat the process. Okay. For the next entry, everything above the main diagonal is going to be 0. The next entry in L2 is going to be 1. And then I need to populate the elements below it. And I'm going to do that by doing the same thing I did here. I'm going to take the element that is in the pivot position of A2. Okay. And I'm going to divide everything below it by that value. And that's what's going to populate the rest of my L2 vector. Okay, so the entries from the pivot position in A at A22 divide the entries below the pivot in A2, and these values form the rest of L2. So again, let's come backwards a little bit. Okay, so to form L1, I took this vector and I divided it by all the things in its pivot position, and that's what L1 column vector was. Okay. Then I zero this out, which is going to change all the rows below it. Okay, and then I'm going to take this vector. Okay, this position in L2 will be 1. This position in L2 will be 0 because the main diagonal is going to be 1. The values above it will be all zeros, right? So in L2, I have the first two terms here. And then all the values below this position, I will divide by A22, the value that's here in this pivot. It will divide. It remains unchanged in my actual A, but those values populate the rest of my L2 vector. And I'm just going to do that over and over again. I'm going to go over here, and in the third term, in L3, that will be 1. All the values above it in my L3 will be 0. And then I take the next pivot, this next pivot position, and I divide all the entries below it by that A33 term, and that is what goes into the rest of the populace for that L3 vector. And I just do that all the way across A until A is done, and that's how I build my L vector, or I'm sorry, my L matrix one at a time. Okay. So I repeat this process until I build it out. So I've done it without doing an actual example, right? So you may still be a little lost, but hopefully when I do it with an actual example, it will make sense and it won't seem too strange to you guys. So I do this, and when I'm done, the A matrix I have will be upper triangular. The diagonal entries will not be 1, okay, but it will be an upper triangular matrix. It'll be in reduced echelon form. My L matrix will be lower triangular, and its diagonal entries will be 1. Okay, so A will be upper triangular, and L will be lower triangular. We then will decompose A by taking those diagonal entries that are not 1 there, and I'll just make those the diagonal entries for A. Okay, these will actually be the eigenvalues of A, and we can, talk more about that, but obviously at this point you guys are pretty familiar that everything is pretty interconnected here in linear algebra. And so that will make my LD, the diagonal matrix made from the diagonal entries of this A that I reduce echelon formed into an upper triangular matrix. And then I'll take this lower triangular and I'll transpose it, and that'll be my LDLT. Okay. So that's what's left of A, right? the reduced echelon form of A that I created. So let's do an example, okay? Let's take, again, we need to have a symmetric matrix for this, okay? So we're going to find the LDLT factorization for this square symmetric matrix, okay? The reason it needs to be symmetric is because if it's symmetric and positive definite, it allows me to have all positive entries left over for that D matrix that I'm trying to form, and that's what we needed, okay? So I'm going to take A and I'm going to build L at the same time as we build A, right? So remember, what do I do first? My first column vector of L will be this column vector divided by what's in the first pivot position. So it's going to be this thing all divided by this 3 here. So it's going to be a 1, a negative 1/3, and a 0, okay? The rest of these are unknown. So take this pivot position for this vector and divide all the values below it by the entry in that position, and that's going to be my first vector. Okay, so first one's always easy to get started on, right? So what I'm going to do now is I'm going to zero out the values below 3. So this one I don't have to do anything because it's already 0. This one I do. So when I do this, I am not going to divide all of this by 3, right? I'm doing a reduced echelon form, but I'm not doing the row reduced. I don't need these to be 1s here, okay? I'm just going to zero out the values. So what I need to do then is the row operation I'm going to do is R2 becomes R2 plus 1/3 of R1. That way this turns into a positive 1, and these things will zero out because I have a negative 1 plus a positive 1. This will go to 0. So this will be 3 plus a negative 1/3, right? So that's going to give me 2 2/3, you know, but obviously we're not writing mixed numbers here. It's not an algebra 1 class, right? So keep that as a mixed number. And then this is not going to do anything because I'm not adding anything, right? So A1. So my next A will have the last thing the same. This is 2 2/3, right? 8/3 is 2 2/3, but obviously we write it as a mixed fraction, or I'm sorry, an improper fraction, not as some, you know, elementary school mixed number, okay? And obviously this one stays the same. So now I can build the next entry, okay? Remember, this is going to be lower diagonal. So this will be a 1 and this will be a 1, and all of these are going to be zeros up here, okay? So I know that for this vector that I'm trying to build, 0, 1, and this is what I'll need to populate, okay? And how do I populate that? I take the entry in that position, okay, and I divide everything below it by that value, just like I did here. I take the entry in the pivot position, and I divide everything by that entry, and that's what made this first one. I'm going to do the same thing here. I'm going to take these, I'm going to divide it by the entry, which is 8/3. 8/3 divided by 8/3 will give me the 1. Negative 1 divided by 8/3 gives me the reciprocal. So this will be a negative 3/8. Okay, negative 3/8. Because I'm dividing negative 1 by 8/3, it's going to flip it around, right? So this next one is the last column. I already know it's going to be 0, 0, 1. That's fine, okay? But I need to keep track of what's going to go on here, okay? Because this matrix is going to be important. I'm still going to use this A. So even though I know what my last L will look like, right? This will be 0, 0, 1 here because it has to be a lower triangular. I at this point have L, but I do have to finish creating my A. So I need to zero out the values below this position now. So I'm going to take R3, it's going to turn into R3 plus 3/8 R2, because that will get these things to cancel out. That'll turn this into a 1 and it'll cancel. And so when I do that here and I do that for this one, we're going to have fractions. You can do this on the side. I did not write out the work, okay, but that's not a hard thing to work on. So again, the equation, the matrix, the row operation you're doing is R3 turns into R3 plus, because it's already a minus, right? So plus, and I need to have the reciprocal of this, so that when I multiply it by here, it turns in. So what we're going to have then is this will zero out, because that's by design, and we're going to get 21 over 8 here. Okay, so now if this was an LU decomposition, I would call this my U matrix because it's upper diagonal, right? And I'll touch back on that in just a second. Okay, and again, we already know what the L is going to look like, right? So now that I have my L and I have my A's upper triangular, these vectors, these entries here are actually the eigenvalues of A. Okay, and if you notice, I did it without actually even finding any determinants or anything, right? Which is pretty cool. All of that has to do with the fact that the determinant of a matrix, okay, is really the same thing as all of its eigenvalues, the product of all of its eigenvalues. So if you took all of your eigenvalues for a symmetric matrix and you multiply them, you're going to have the same thing as the determinant of that matrix. Okay, so that's why, because if I were to try to find the determinant now that it's in one of its triangular forms, I would just multiply the main diagonals, and that's going to be the same thing, the same value as if I were to find the product of all of its determinants. So that's why that works. Okay, so now I have L, I have my A, and let's start to break things down, right? So my L looks like this. My diagonal matrix is going to be made up of the main diagonal entries of this A. Okay, so 3, 8/3, and 21 over 8. That's how I form my D. I'm just pulling these values out and I'm putting them in order. And then the last part, the L transpose, is just the transpose of this matrix. Now if I multiply all of these out, I will get A, because that is my factorization, right? So if I multiply all these out, I get my A matrix out, right? Now let's talk about some of the things I touched on briefly here, okay? Because there's a lot of stuff going on in here as far as other decompositions. So this LDLT composition it already has a subcomposition already. This DLT is my A matrix that makes up LU decomposition. So we're going to talk about that a little bit more with some notes here. So the diagonal entries of L are all 1, and the entries of D are all positive, and they're positive because this is a positive definite matrix, right? So the last form of A would be our U in an LU factorization. Okay, so if we were doing an LU factorization, this would be my U, right? If I go L times this reduced echelon form of A, I would call this my U. So L times U would get me back my original A as well, which we are actually going to show right now. Okay, so if I did L times U and multiply that out, I would get A again. Okay, so that is this factorization is the factorization that we skipped over earlier in the semester. You can go back and look through your textbook. It's towards the beginning of the textbook, is around the determinant section. Okay, DL transpose, the D matrix, and the L transpose, this one transpose, if I multiply that out, that is my A, right? So remember, I took the entries here and I was like, just throw them into a matrix, that'll be your D. Well, what's left over when you do that is this L transpose. Okay, so we actually, just by me saying, hey, take these things and throw them away, or not throw them away, but put them in a separate matrix, you kind of just, I basically told you how to find your DLT kind of factorization of this reduced echelon form. Okay, so that would be that U matrix from up here. Okay, now let's talk about one last decomposition. It's called the Cholesky decomposition. And actually, in order to find this decomposition, you would need to find your LDLT decomposition first. Okay, So we call LC, or the lower Cholesky decomposition. This is L times your D raised to the 1/2 power. So 1/2 power is the same thing as square rooting. So remember, for a diagonal matrix, if you're raising it to a power, you just apply that power to the diagonal entries. That's not true with any other kind of matrix, only diagonal matrices, right? If I try to do D cubed, I would cube all of these entries, okay? So here this is to the 1/2 power, right? So then I can take my A equals LDLT, and I can break this down. So basically what I'm going to do is I'm going to take this D to the 1 power, and I'm going to split into 2 parts, right? I'm going to turn it into an L, D1/2 LT. Okay, so again, if I were to multiply this out, I would get the D, and I'd have my the D diagonal matrix from the LDLT factorization. So now if I group these together, okay, I can reverse the order of this D to the 1/2 and L, and I can pull the transpose out by reversing the order. Okay, and the reason I do this is because what is LD to the 1/2? That's just LC. So this is lower Cholesky times lower Cholesky transpose. Oops. Okay. So my A can be decomposed into these two terms. Right, so let's do this on my previous example. We already have all of our stuff, my L, my D, and my L transpose. So let's do all of that and form this decomposition. So again, you need to find the LDLT first. Okay, so let's find the Cholesky decomposition for the matrix we have already, which is this A matrix. Okay, my LC is going to be L, that lower triangular, times the diagonal matrix to the 1/2 power. So I'm just going to square root those entries I had. Okay, so again, I'm just taking these entries and I'm taking their square roots. Okay, all right. So if I multiply that together, that will be my LC, my lower Cholesky triangular matrix. Right, so lower triangular matrix. Now if I transpose that, that's my lower Cholesky transpose. And if I multiply these two, I should get back A, which I do, right? And those are our decompositions.